In the last video, we introduced the concept that OLS estimates are random variables and they have their own distribution. In this video, we will derive the distribution properties of OLS estimator and build confidence intervals and talk about hypothesis testing. It's better to start with the general closed form expression for OLS estimate that we derived. It requires a little bit of matrix manipulations, but it's not rocket science. Now let's calculate the variance of OLS estimator. Note that in the variance calculation of beta hat vector, x is fixed. The randomness is in y, which is caused by u, the error term. So let's just replace the term involving x as constant c for ease of calculation. So here we will assume constant variance for y given x as sigma squared. Note that sigma squared would also be the variance of the error term u given x. This is called constant conditional variance of error terms, also known as homoscedasticity. And simplifying, we get a nice compact expression for variance of our beta hat vector. We call this the variance covariance matrix. We can now also derive the expectation of beta hat vector. And using the zero conditional mean assumption, we get the expectation same as the population parameter. We call this property unbiased. It means that the distribution of the estimates are centered at the population parameters. Let's look at the exact form of the variance covariance matrix for simple linear regression in a slightly elaborate form. We have seen these calculations before, so I'm going to skip through the explanation. And here we get the variance covariance matrix for our beta hat vector. Unpacking the matrix, we get the individual variance for the beta estimates, as well as the covariance between the beta estimates. SSTX is the shorthand for sum of total squares in x, which is the term in the denominator. These formulas give us some valuable insights. The first observation is that the variance of the estimates contain the variance of the error term in the numerator. So the uncertainty from the error term has trickled down to the uncertainty in the parameter estimates. It's like a chain reaction of uncertainty. It started with u, the patient 0, if you will. Then y got affected with the same uncertainty, sigma square. Then the parameter estimates got hit. Although not with the same severity, there is a compression in uncertainty on the parameters, thanks to the OLS estimator. But is it the best compression possible? We will see that in a little bit. The second observation is that if SSTX, which is in the denominator, is equal to 0, then variance becomes infinite. We cannot allow that. It means that x must have some sample variance. I'm not saying that x is a random variable. X is fixed and given, but in the sample, it cannot be a constant for all observations. It has to have some sample variance. Also, the sample variance in x is actually a good thing. Higher the SSTX, lower is the variance in the estimators or uncertainty. Visually speaking, if x has low variance in the sample, that means data is concentrated at a given value of x, then for a different sample of y, we can get a dramatically different pair of estimates. That indicates a lot of uncertainty in the parameters if x is concentrated. On the other hand, if x is more spread out in the sample, then the estimates won't change as much if a different sample for y is used. In the second case, the line has to pass through an entire range of averages and so has little flexibility to move. The third observation is that when we use a large sample, that is n tends to infinity, all of these variances shrink to 0. We already know that the OLS estimates are unbiased. So with n tends to infinity, these estimates will collapse onto the population parameter. We call that property consistency. We talked about several assumptions and properties of OLS. There is a famous theorem that goes by Gauss Markov theorem, which states that under certain assumptions, OLS estimator is blue. First, let's understand the assumptions of Gauss Markov, and then we will talk about what blue means. First assumption is that the model must be linear with respect to parameters. It means that the variable x can take other forms, and that is not a problem as long as we can transform and replace those variables to retain linearity. For example, if we want to include, say, x square as a regressor, then we can simply treat x square as another variable z, and the model will be linear with respect to z. What is not allowed, however, is that the model cannot be non-linear in terms of parameters. So for example, if we want to include a term beta 1 square, then that's not allowed. The second assumption is that sample must be obtained in random. This is needed to satisfy some statistical properties. Third, x must have sample variance. If x is constant, then we get infinite variance on OLS estimates as we saw before. Fourth, zero conditional mean. This is the bread and butter of OLS estimator. It is the one that we started out with, and it's the mother of all assumptions. 5. Homoscedasticity, or constant variance of error terms assumption. We spoke about this before. Again, we are not saying that the conditional density of error terms is the same for all x. Here we are saying only that the conditional variance of error term at each x is same. Note that till now we have not specified that error terms have a normal distribution. Now, what does blue mean? We have to read it in a slightly different way. Consider the universe of all estimators, which can take the data x and y and spit out the parameter estimates. Within the universe of all estimators, consider the class of linear estimators, which are linear with respect to the observation y. Recall that OLS is a linear estimator. Within the class of linear estimators, consider only those ones which are unbiased. Note that the graphic does not mean that all unbiased estimators are linear. What we are trying to say is that only consider the unbiased estimators within the class of linear estimators. So finally, within the class of linear unbiased estimators, OLS is the one with the minimum variance. That's what best means. Note that only the first 4 assumptions are needed to prove that OLS estimator is unbiased. We use the 5th assumption to derive the variance of the OLS estimates. So we have the mean and the variance of the OLS estimator, but we don't know the type of distribution it follows. If we can get the sample distribution of OLS, then we can build confidence intervals, do hypothesis testing, etc. So that's why we add another assumption, number 6, is that error terms are normally distributed. Note that normality was not needed to prove that OLS is blue. These 6 assumptions together are called as classical linear model assumptions. But wait, we are assuming error terms have a variance of sigma squared. Do we know sigma squared? We don't. Do we observe the error terms? We don't. All we have is the fitted error terms or residuals or U hats. So we can use those to calculate the error variance. The error variance sigma hat squared is the sample variance of the residuals. Note that the sample mean of the residuals is 0, so the numerator is simply sum of square residuals. The one caveat here is that the denominator in case of simple regression is n minus 2 instead of n. This is called as the bias correction. If you remember, when we calculate the sample variance as an estimate for population variance, we correct the bias by changing the denominator to n minus 1. The reasoning there is that the formula uses sample mean x bar as an estimate for population mean, and the calculation x bar consumes 1 degree of freedom. Similarly, in case of error variance calculation, we lose 2 degrees of freedom because there are 2 constraints on the residuals. And those constraints are imposed by OLS procedure. Number 1, sum of residuals is 0. Number 2, residual vector is orthogonal to x. Or you can say that the sample covariance between x and u hat is 0. So now we have an estimate for error variance as well. It can be shown that the above is an unbiased estimator for error variance. Sigma hat, which is the square root, is called as the standard error of regression. Note that SER is a biased estimator for sigma hat because expectation of a square root is not the same as square root of expectation. Now that we have estimated sigma, we can replace this estimate in the variance formula for OLS estimates. The square root of the variance of estimates is called as the standard error of beta. Alright, we got the estimate for OLS variance. What's next? Well, now we can specify the complete distribution of the beta estimates. Now we have assumed that the error terms have normal distribution. It's actually a very strong assumption. Notice that stating that error terms have normal distribution everywhere encompasses both the 4th and 5th assumption. If u is normal, y is also normal. Of course, mean of y depends on x, so we can say y given x is normal. OLS estimate beta hat is linear in y. That means beta hat is also normally distributed. Let's write these distributions individually for our OLS estimates in case of simple linear regression. We can also write in terms of Z transformation that follows standard normal distribution. Here the only problem is that the variance sigma squared is unknown, but we do have an estimate for it. So when we replace the unknown variance sigma squared with its sample estimate, the normal distribution becomes a t-distribution. In this case, the t-distribution will have n-2 degrees of freedom. Notice that the square root term in the denominator is nothing but the standard error. Of course, for large sample size n, the t-distribution approaches normal distribution. But this right here gives us the recipe to build confidence intervals around the beta estimates and perform hypothesis testing. Once we estimate beta 0 hat and beta 1 hat from the sample, we can, let's say, create a 95% confidence interval for the true population parameters. Here I have used a factor of 2 to approximate the confidence interval on either side. For the exact confidence interval, we have to invert the t-distribution, keeping the 2.5% probability on each side. We can also perform hypothesis testing. For example, the null hypothesis could be that there is no relationship between x and y, which indirectly means that beta 1 is equal to 0. The alternate hypothesis would be that beta 1 is not equal to 0. Since our statistic follows t-distribution, we simply need to do a t-test. Here our hypothesized parameter is 0, so our t-stat is given as this. We can calculate the critical values from the t-distribution with, let's say, 5% level of significance, which means that 2.5% probability on either side for a 2-tailed test. If our t-stat from the sample falls within the critical values, then we do not reject the null. If it falls outside the critical zone, also known as the zone of rejection, then we will reject the null. Rejecting the null would mean that we are rejecting beta 1 equals to 0, which means there is significant association between x and y. Not rejecting the null means that the relationship between x and y is not significant. We can also decide to reject or not reject based on p-value. P-value is the total probability of observing a value more extreme than the t-stat. So in a two-tailed test, the p-value is given by 2 times the area to the extreme of the t-stat. It means that if the t-stat is negative, as is in this case, p-value would be twice the left tail probability of the t-stat. If the p-value is less than 5%, which is our level of significance, then we say that p-value is significant and we reject the null. If the p-value is greater than 5%, then we say that the p-value is not significant and we do not reject the null. Similarly, if the t-stat is positive in this, as is in this case, p-value is twice the tail probability to the right of t-stat. If this p-value is less than 5%, we say that p-value is significant and we reject the null. Similarly, if p-value is greater than 5%, we say p-value is not significant and we do not reject the null. We can perform directional hypotheses such as beta 1 is less than or equal to 2. We will perform a one-tailed test in this case. So calculate t-stat from the sample as usual. Notice that here our hypothesized parameter value is 2, not 0. As per the null, beta 1 is less than or equal to 2. So if the sample gives us a value that is ridiculously larger than 2, then we will reject the null. That means our zone of rejection would be on the right-hand side. And we would assign the whole 5% probability on the right-hand side. Accordingly, the critical value can be found by doing T inverse 95%. So if the t-stat from the sample falls outside of the zone of rejection, then we do not reject the null. Notice that in this case the p-value is simply the area to the right of the t-stat, but rest of the logic is the same. And if it falls in the zone of rejection, then we reject the null. That's all for now. Thanks for watching. If you liked the video, please subscribe to this channel to get latest educational content on statistics, finance, risk management, and analytics. Also, if you are a finance professional and looking for a certification in data science, log on to peakstotales.com and check out our prep course for Finance Data Professional, which is a global certification offered by FDP Institute. Experience a new way of learning complex mathematical and statistical concepts with rich visualization in an easy-to-follow Microsoft Excel-based environment. Take advantage of our mind maps and Excel-based hands-on modeling sessions.